let's do. What's the equation for interference? M lambda equals d sine theta. And what kind of interference is this? Was it constructive? Constructive. So constructive interference, is that bright or dark spots?
Bright.
So this is bright spots. And what is M for this interference?
Order.
M is the order, and what can it be?
0.
0.
-1.
Positive or -1, positive, -2, etc. So this is interference. This works with 2 slits. What about 3 slits? So we know it works with this. Does it work with this? Yep. Does it work with this? Yep. Does it work with this? Yep. This works with multiple slits. Once 2 slits, 3 slits, 4 slits, 5 slits, as many slits as you want. M lambda equals d sine theta gives you constructive interference. It lets you find bright spots. If I want to find dark spots in an interference pattern, can I use this equation? Huh? Kind of. What do I need to do about this? I need to change something in this equation. It's what? If I want to find interference, dark spots in interference patterns, multiple slit interference patterns.
Is it 2D?
It's what?
2D.
Nope. M plus 1/2
Oh.
times lambda equals d sine theta. I know what Maya was thinking about. She's a step ahead of me. This is destructive interference. This lets you predict the dark spots for multiple slits. Dark spots. And M is again 0, plus or minus 1, plus or minus 2, etc. Okay? So I can find bright spots, I can find dark spots, and this works with multiple slits. And the way this bottom one works is for getting destructive interference. Remember, I've got that pattern that I can draw, and I have a bright spot, and then I have a dark spot, a bright spot, dark spot, bright spot, dark spot. Kind of looks like this. And these bright spots and dark spots are happening because of wavelengths, because wavelengths interfering with each other constructively or destructively. So if I have 2 waves, wave goes up, down, up, down, up. Let's have another wave up, down, up. And I look at these 2 waves. Right here at the last point, I have this wave on an upshot, this wave on an upshot. Right? They're both ending at the top of a wave, so they're going to constructively interfere with each other. Does that make sense?
Yes.
Yeah, we can see that. Now let's say that I go with this bottom equation, M plus 1/2. So what I'm going to do is add half a wavelength to this. So if I add another half of a wavelength, that brings me down to here. Now I have the top of one wave is meeting up with the bottom of another wave. What's that going to do? Cancels out. So that's literally what's happening. We're fitting an extra half wavelength in, and because of that, the waves will cancel out. So we get these dark spots. Yep. So this very naturally extends into diffraction. Diffraction is what we get with a single slit. So when you're seeing interference patterns, there is diffraction superimposed on that, because each single slit has diffraction that happens. We get a single little hole that we travel through. We got a screen. Screen is a distance, we'll say D away. Uppercase D. The size of the slit here is going to be A. So instead of lowercase d for the separation of slits, we're using A for the size of that slit, the size of the open space that light is coming through. And we got bright spot, dark spot, bright spot, dark spot, bright spot, dark spot, so on and so forth on either side. This pattern looks very, very similar to the interference pattern. the physics of what's actually happening, it gets a little bit complicated and a little bit weird. You've got light from the top of the slit coming and striking the screen, and then you have light from about the middle of the slit coming and hitting that screen. And you take this picture, and if you blow it up, you can do some geometry. Your book does these calculations for you and shows you these pictures. If anybody wants to see more detail of it, just let me know, and we can talk about it offline. But this gives you an equation. An equation that looks very similar to one we just talked about. It gives us an equation, m times lambda equals a times sine of theta. We'll do some rough approximations to get an idea of what this picture kind of looks like. We can assume the central spot, that's the distance d, and then the theta that we're talking about is the theta to the now space in between the bright spots. So that's where the light is canceling out. And that height up to your dark spot, we'll again call that maybe y. The big difference here between diffraction and interference. This diffraction equation, it looks like the interference equation, doesn't it? Looks like the interference equation for getting bright spots. But in diffraction, when you're just talking about one slit, this is telling you where the dark spots are. So for single slit diffraction, these are dark spots. This is destructive interference. And m, in this case, doesn't start at 0. It's positive or negative 1, positive or negative 2, so on and so forth. Okay. That's going to be the biggest thing that messes people up, is this equation works for a single slit, and it tells you where the dark spots are. There is not an diffraction equation that will give you the bright spots and the bright spot locations. But everything else, all the geometry and stuff, still very, very much the same as interference. Okay? This is the single most confusing thing that I could find in diffraction and interference. So you have a worksheet to do about this for your in-class assignment. And I just want to solve one of those problems. And I just picked out the middle one, problem number 4. So let's do problem number 4 together. Problem number 4 from your worksheet. We have monochromatic blue light of unknown wavelength. Okay, so unknown wavelength, right away I know theta is something that I'm looking for. Theta is an unknown. And this light shines on a slit that is 0.052 millimeters wide. 0.052 millimeters is the width of the slit. So what variable is that? Is that A or is it D?
D.
This is A. Width of a slit is A. Separation of slits is D. They say that it's one slit, so that means that it's going to be A. If there's multiple slits or slit separations, then it's going to be D. So what kind of spots am I going to have to be finding here? Am I going to be finding bright spots or dark spots?
Dark.
I'm going to be finding dark spots, hopefully. If this is an A, then I can only find the dark spots. Okay, that slit is 0.052 millimeters away. What should I do with this 0.052 right away? Convert it to what? Meters. So that's 0.052 times 10 to the negative 3 meters. It's on a screen that's placed 1.15 meters from the slit. So what variable is that? This is from the slit to the screen.
D.
D, capital D, is 1.15 meters. The first dark band, aha, there it told us, dark band, that means it's a dark spot. And which dark spot is it? It's the first. What does that tell you?
M1.
Tells you m equals 1. So many clues in these problems. and it appears at a distance of 10.1 millimeters from the central bright line. What variable is that? Somebody said it. I heard a Y. It's 10.1 millimeters. Bless you, somebody that sneezed. So 10.1, I want to convert that into 10.1 times 10 to the negative 3 meters. Use that to calculate the wavelength of the light. Okay, let's draw a picture of what this looks like. So I have a single slit. I'm going to shine some light. That light's going to shine and find a dark spot somewhere up here. I have this distance. This is my angle theta. This is my Y. This is my D. D is 1.15. Y is 10.1 times 10 to the negative 3. What equation can I use here? What equation?
Brack equation.
Brack equation. So Brack equation is for a crystalline structure. So is that going to, do we have a crystalline structure here? Nope. I'm getting a diffraction pattern. What is the equation for single slit diffraction? M lambda equals A sine theta. I'm looking for lambda. So let me divide both sides by M. M's cancel out on the left-hand side, so I get the wavelength is A sine theta over M. I know what A is. They gave us that in the problem, 0.052. Sine theta. Do I know what theta is? Can what? I can calculate it? How can I do that? I have a right triangle here. Damn it, the right triangles from the very first day we ever did physics, they're still back. We can't get rid of those frickin' things. So, I can use a trig function to find this. What trig function can I use?
Sine is opposite over.
Sine is opposite over a hypotenuse. Do I know the hypotenuse length? Nope. Tangent? What's tangent? Tangent theta is opposite over adjacent. So I can use tangent of theta is equal to 10.1 times 10 to the minus 3 divided by 1.15. I take the inverse tangent of both sides so that I find theta is the inverse tangent of 10.1 times 10 to the negative 3 divided by 1.15. Steal your neighbor's calculator and calculate what theta is. And you'll find theta is really, really tiny, I think. I got 0.5 degrees. What mode do you need to make sure your calculator is in?
Degrees.
Make sure you're in degrees. Plug it in. If you want to know if you're calculating angles correctly, you should get theta equals 0.5. If you're not getting 0.5, come ask me about it.
Opposite over adjacent.
So then I can take that and I can plug that in for theta. And I know what my M is, so I can plug in all of my variables now. A was equal to, they gave us in the problem, 0.052 millimeters. So I multiply that times 10 to the negative third to get it to meters. Times sine of 0.5. And I divide by the order. This was the first dark spot they told us in the problem. So I get the wavelength is about equal to 4.65 times 10 to the negative 7 meters. And that's supposed to be blue light. Is that blue light? I got a laser. That's blue light. Is that blue light?
Yeah.
they give us the wavelength?
495.
450 and 495? Am I between 450 and 495? Yay! Blue light, it all makes sense. Physics works. We didn't break the universe. In this problem. Any questions about this problem? And you've got worksheets to continue solving all of those. I think there's 8 more of those to do.
Does this do at the end of class, or do we have to? We have to-
Before the end of class. And then you've got to read a paper about photo 51. Did you learn about photo 51 in your biology classes? What is photo 51 about? DNA. What shape is DNA? Double helix. What shape is a spring from a pen? It's very similar to a double helix. So while you're working on stuff, I can't show you as a class. I'm going to come around and show you how it kind of works. Photo 51. Okay? That's all I've got for you for in-class. If there are no questions, go ahead and get started on those in-class problems. And I'll be around.